Alrighty, sweet peas, we're going to look at graphing log functions by hand, and we're going to start by remembering some of the transformations that we discussed. Transformations are awesome because they allow us to know how any function is going to behave based on patterns. So let's kind of think back on what we know. We know that A out front allows us to see how something is stretched or compressed. So here's A. And if we look at A, we know a few things. Here we go. Here's A. So when A is less than 0, in other words, when it's negative, this causes the entire function to reflect over the x-axis. Over the x-axis. In effect, it gives a mirror reflection, or the log graph appears to turn upside down. When the absolute value of A is greater than 1, whether it's negative or positive, if it's greater than 1, then we have a vertical stretch, and the y values get further away. They're stretched up further away from the x-axis. When the absolute value of A is less than 1, that is when it is a fraction between 0 and 1, then we have a vertical compression or a vertical shrink, and the y values get mashed down closer towards the x-axis. So you can call that a compression or a shrink, either one, whichever speaks to you. The b right here in our log equation is the base, and we'll use that to find our guide points. We're going to come back to c. He's the new player. We haven't looked at him before. Inside the parentheses, a change of adding or subtracting to h creates a horizontal shift, and if you have x minus h, that shifts to the right. H units. If you have x plus h, that shifts to the left. H units. And that's backwards in what we're used to speaking, but when you change x before you do the function, it creates a horizontal change. The plus k at the end gives us, honestly, our vertical shift up or down. On the log function, it also allows us to know where the the vertical asymptote is. So plus k, wait, I think I said that wrong. I did say that wrong. The x minus h allows us to know where the vertical asymptote is. The plus k just gives us our vertical shift up or down. So plus k shifts up, k, and minus k shifts the whole function down, k units, from where it is on the mother function. C is the new player. C creates a horizontal stretch or compression. If C is less than 0, this causes the log graph to flip or reflect over the y-axis. So a negative c causes it to reflect over the y-axis. If c is greater than 1, this causes a horizontal compression. And I know that's opposite from what we know about vertical stretch and compression, but we talked about that it was like a slinky, that if you have to squeeze 3 times as many curls into the same space, that you're going to have to mash the coil or the spring or the curls together. When C is less than 1, it becomes a horizontal stretch. So, just kind of recapping our transformations that we can have to a log function. The log graph, when we're graphing by hand, when the log is in base B, the graph goes through 3 guide points. And these guide points should seem familiar. You've seen something like this before when we did exponentials. In fact, each point is an inverse of the exponential points. The first point is 1 over b and -1. Then it goes through on the x-axis 1, 0, and then the point b1. So this is what we refer to as our guide points. 1 over b, -1, 1, 0, and b1. And these are the 3 points that we have for every single log function. And again, the b is the base, which is given to us in the equation. Our vertical asymptote on the mother function is at x equals 0. The domain is the restricted part here. The domain is strictly greater than 0. As you see on this curve, it comes down and snugs right up against the y-axis, but without ever touching it. And our range is unrestricted. Our range now goes from positive to negative infinity. All right, so now it's time for us to look at a graph in particular. We looked at a few in class. We're going to look at this one because it has something interesting. If you will look inside the parentheses, you will notice that you have 2x minus 2 in the parentheses. And what we need to be able to do is to figure out what c is, and does that affect our h value? So let's go in and start to identify, based on what we know about transformations, can we tell what the a value is? And remember, a is the coefficient out in front of the log value, or the word log. We don't see anything out there, so of course we have an understood 1. Then we look for our base. In this one, our base is 3. And then we start to look at c. Well, c is our new friend, and in the pattern, it shows c parentheses x minus h. We don't have a number in front of the parentheses, but look inside the parentheses, you see 2x minus 2. Think back to 7th grade when you learned the distributive property in factoring. 2x minus 2 can be broken apart, and if you look closely, you'll notice that it has a common factor of 2. So when we pull out the 2, we're left with x minus 1 in the parentheses. And now the argument, that is the thing that we're taking the log of, jumps out at us in that pattern form, and we can identify that c is 2, and that h, our horizontal transformation, is actually plus 1. So be careful. If you have something in parentheses, look and see, can I factor it? Can I take out is there a coefficient in front of my x value that I need to factor out? Because that will affect your horizontal transformation when you go to graph it. If you look at the end, you see a 3, and that is our vertical shift. So let's use these in our little graphic organizer to go in, find our guide points. Remember, the mother function goes through 1, 0, then it goes through b1, and in this case, our b is 3, and then it goes through 1 over b, -1, so that would give us 1/3. Alrighty, so let's go in and do our magic here, except of course it's not magic, it's just good transformations. Multiply y by a equals, in this case, 1. And let's remember what we know about multiplying by 1 is the multiplicative identity, which means I can always multiply by 1 and it doesn't change the outcome. So 1 times anything is, of course, itself. You can go in and identify the y values by 1 if you like, or you can just know it's not going to change. Alrighty, so I still have 1, 0 as my point. Now I'm going to divide by the x value by my c, and I factored out 2 as c. So 1 divided by 2 becomes 1/2. Now I'm going to add h to x. So my horizontal shift is 1 to the right. So 1/2 is now 1 1/2. and I'm going to add k to y. My k value is 3. So I have 1.5, 3. And we can go over and plot that point, 1.5 and up 3, about right there. Let's decide where our asymptote is. I like to do that first, and I should have done it this time. Remember, our asymptote when we do logarithms is based on my my h shift right here, x minus 1, so that means I'm going to shift to the right 1. So instead of my asymptote being at x equals 0, it's now going to be at x equals 1. So let's come in and go ahead and put our vertical asymptote right there at x equals 1. And already we see, is this behaving like we think? Well, we can visually remember what normal, the mother function of logarithms look like right here. This one appears to be going, up 3 without a vertical stretch and 1 to the right. So, yes, it does look like what we probably think that it should look like. We can go into the other points. Again, multiplying y by 1 doesn't change it. Dividing 3 by 2 gives us 1.5 or 3 halves. Adding 1 to x now gives us 2.5. And then adding 3 to 1 gives us 4. So our next point to plot is 2.5, 4. 2.5, 4. And sure enough, it's right there on the curve following the pattern that we would expect. And then the very last one, 1/3, -1. Multiplying -1 by 1, of course, does not change it. Dividing 1/3 by 2. Remember, dividing is multiplying by the reciprocal, so we can come down here and visually remember 1/3 divided by 2 is 1/3 times 1/2, which is 1/6. All right, so 1/6 and -1. Then let's add 1 to 1/6, and we get 7/6, or 1 1/6. -1. That is not very neat looking. Sorry about that. Tried to make it better, and I think it looks worse. All right, 1 1/6 and -1. And then the last one, I'll try to make this one a little neater. Add 3 to y. -1 plus 3 is 2. So we have 1 1/6. That's better. And 2. So let's come over here. 1 1/6, just a hair away from the asymptote, right there. And then we were given this other point, so what do we want to do? We want to try to connect all of these in a smooth curve. And shazam, something like that. And that is how we take each of the log functions and graph them using our little organizer here to help us generate the points by hand. The range, of course, is always all real numbers on all log functions. The domain is restricted. It's based on our horizontal shift. In this case, if our horizontal shift is right 1, then our domain is just greater than that. X greater than 1. All right, so our very last graph that we're going to look at today doesn't have all of the transformations, but it has a few. It does have a different one. Primarily this one, if we notice right away, we have a negative out front of the log word. So that means that our A value is -1. And wonder what that's going to do. Our base is 4. C. Remember, C is our new transformation that we're exploring in logs, and C is found out in front of the X. There is a 2 out in front of the X, but notice what is missing. We don't have parentheses around the X and the -1. So if you think about that, when we looked at them before, the parentheses helped us see the horizontal shift left or right. If we don't have parentheses, then we can assume that there's not a horizontal shift, that the -1 at the end is specifically a vertical shift up or down. So for our class, I will tell you that if there is a horizontal shift, there will be parentheses at least around the X, and not, you won't have to guess and say, well, is this a 2? Do I factor the 2 out from the -1? No, we can trust that this is going to be a vertical shift at the end because it's not a change inside the function. What we're doing here, if you think about order of operations, I'm taking the log of 2x, then I'm making it negative, then I'm shifting down 1. So there is not a horizontal shift in this one. It's a small, minute difference, but the parenthesis placement is very important. This doesn't have parentheses, so we know, hey, this -1 is vertical, it's not horizontal. Okay, so finishing, we see that C is equal to 2. There is no horizontal shift. You can put a 0 here, you can leave it blank, doesn't matter. We don't move from the mother function placement of being snug up against the y-axis. Then our k value is -1. So since we have no horizontal shift, our asymptote is in the same place at x equals 0. So if you want to, you can come right down here on the y-axis and put your asymptote at x equals 0. I think this time I'll change colors. Let's go with the red. That'll show up nicely. And go in and remember our guide points. We have 1, 0. We have B1. That's not a 6. Somebody asked me that the other day. No, that's a lowercase b. And so for base on this particular problem, that's 4. And then 1 over b and -1, so 1/4. We're going to multiply y by our a value of -1. So -1 times 0, of course, is still 0. Now we're going to divide our x value by c, which is 2. And when we divide it by 2, again, what does that get smaller? So we're looking at what? A horizontal compression. So when we divide c by 2, or divide by c equals 2, we get 1/2, 0. And then we add h to x. Our h value is 0. 0 plus x is still 1/2. Adding 0 doesn't change anything. So once again, we see a column where it's here to teach you that you might have an h to add or subtract. But in this case, of course, we don't. So somebody asked me yesterday, do we have to go ahead and put that in if it's not going to change it? No, you don't. All right. Whatever helps you understand it best. Then let's add -1 to the y value. So we have 1/2 and -1. Going back, we'll make the same changes. But before we do that, why don't we plot this point? 1/2 -1. So 1/2 -1 right there. And we see there's already a point on the graph. We know what the mother function looks like. And we remember that there is a minus out front. So this time the log tail is going to be up in the air and then flap to the right. And so far, it looks like that might be exactly what's happening. Let's take 4, 1 through the points here. When we multiply by -1, we get 4, -1. Then when we divide 4 by 2, we get 2, -1, and you see right there, that causes a shrink. It was 4, it's now at 2. Now we're going to add 0, and of course that doesn't change things, and then add -1, and we get to -2. And we plot that point to -2 right there, and we see the curve taking place. Lastly, 1/4 -1. We're going to multiply the a value by -1, and we get, we're going to multiply y by the a value of -1, and we have 4, 1. No, that's not right, is it? I need my alert students here. I'll just find the eraser. Aha. I need my alert students here to keep me on track. Alrighty, so this would be 1/4. There we go. 1/4, 1. The next one, we're going to divide 1/4 by 2. We practiced this a while ago. Dividing by 2 is, of course, multiplying by the reciprocal. All division is that, not just fractions. All division is multiplying by the reciprocal, and we get 1/8. 1. Then what? Add 0. Of course, it's still 1/8, 1. And then let's add -1 to the y value, so we get 1/8, 0. 1/8, whew, right there, 0. Almost right there. So our range, just like all log functions, our range is all real numbers. Again, you can write that with a double bar R, or we can put it in interval notation, of course, -infinity to +infinity. The domain is strictly greater than the asymptote, so we're going to say x greater than 0. Let's come down here, snug right up against that y-axis, and then start to curve. And we'll come around like this, and a little bit further to this last guide point that they've put in. And there is our curve. Tomorrow we'll talk about using our graphing calculator to check on these after we've learned some of the properties and we understand logs better, but you've done a great job using transformations to graph logs by hand. Thanks, sweet peas, and we'll talk more math soon.